for the invitation and the introduction. It's an honor to speak at IAS. You should feel free to ask any questions and also questions regarding to the proof. The purpose of this talk today is trying to convince you that there is actually a proof. Hope I can succeed, but I'm not sure. So let me first give you the setup. Let's say lambda n is a box on Z2. Let's just for concreteness, let's say it's centered at origin O with let's say side length 2n. And I will use this notation, partial lambda n to be the outer boundary of lambda n, and I can use this for outer boundary for any other set too. And we will consider HV to be HV for V is a vertex on Z2. These are IID, identically distributed and independent. I just in case there are audience in the not from the probability side. The IID are normal variables with mean 0 and variance sigma square, and variance epsilon square. Epsilon is positive, but can be very small. And actually, the main point for this talk is that epsilon is very small for our case. And then we consider the Hamiltonian for the Ising model. This is defined to be, well, we consider a configuration sigma that is taking values plus minus for each vertex in the box. And we can consider the Hamiltonian with a plus boundary and a minus boundary condition. This is just, you look at all the pairwise interaction in the box. And you also look at the interaction with the boundary. So this is when one vertex, this is when UV is a pair of the edges crossing the boundary. And also take into account of the interaction with the external field. So this is the Hamiltonian, and with this Hamiltonian, if you can consider any temperature and define, let's say non-negative temperature, and define a measure, an Ising measure. But the main focus for today is going to be just at 0 temperature. So for this purpose, the measure we just need to consider the ground state. So let sigma lambda plus minus. This means with respect to plus boundary and minus boundary condition respectively. Let this to be the ground state, namely those are the minimizers of the Hamiltonian, and with the probability 1, this ground state should be unique. Now I'm ready to state the theorem for today. This is the Hamiltonian. Yeah, this is with the plus boundary condition or with the minus boundary condition. And the ground state is also with the plus boundary condition, minus boundary condition. You can consider other boundary conditions, but these are the two things that matters for us. The theorem says that for any positive epsilon exists a constant positive such that the probability that the ground state does not agree at the origin decays exponentially. And this implies that the spin correlations decays exponentially also. Now let me give you some background. Yeah.
Are you able to say anything
about the C of epsilon?
Yeah.
Good question. In order to say something about C of epsilon, you need to say something about what Mike and Bocha did for this percolation exponent. At the moment, no, but maybe it's possible, but it requires work. I will give a remark when it is at the right place.
Okay, what does it mean at 0 temperature?
0 temperature just means I look at the ground state.
Looks at the minimizer.
I just look at the minimizer of the Hamiltonian. At the positive temperature, you could put a measure as e to the beta times the Hamiltonian, and the probability is proportional to that. But imagine beta is the inverse temperature. Imagine beta is infinite, then this is put just on the ground state. And since I give you a continuous external field, the ground state is unique. Does that make sense? So now some background. This is under the umbrella of the Imre-Mar phenomenon. In 1975. And there has been actually quite a few mathematical works, and the previous mathematical works. Let me focus on the random field Ising model. The Imre-Mar phenomenon is more general, but let's just talk about Ising model today in 2 dimensions. Well, okay. Yeah, let me even focus on 2 dimensions. I don't want to discuss too much of the literature. And all the previous work works for all non-negative temperatures. And there has been a sequence of works. There is the groundbreaking work of Ising, and where in 90s. I think it's 1990, and it shows that this decays is 0. And that is actually applies to more disorder. I think it's all disorder. Well, our work did the Gaussing.
What decays to 0?
The same thing. The same thing, but you.
Probability
Yeah.
it just didn't show.
Well, yeah, right. But if you at a positive temperature, you could look at this as the difference of the spin correlations.
Yeah.
Sorry, the magnetization at plus boundary and minus boundary. You could just interpret the result in the special case of 0 temperature. It doesn't lose, yeah. For the purpose of the talk, it's fine, I think. And this has been improved by Chatterjee after a long time. It's 28 years, and it shows that it's less than 1 over log n. And then shortly after that, I with the pellet in the same year. It shows that this is bounded by some power law. The C of epsilon is positive, but the C of epsilon in this case is very small. If the power is large, say larger than 1, then it's finished. But what they can get here, the C of epsilon is small in epsilon. These 2 works did Gaussian orders. I think used some properties of Gaussian processes, like for us too.
You need the Gaussian structure?
We need it for a couple of we need the Gaussian structure in a couple of places. Like the change of measure has a much nicer form, and it's also easier to understand. There's a linear decomposition for Gaussians. If you can condition the linear statistics, you know what it is exactly. And I'm happy with the Gaussian for now, so we didn't even try to do more. There are also a number of works that proves exponential decay when the disorder is large. If the disorder is large, you have exponential decay. This has been done in Berretti in 85, Froelich Embre in 84, and Camille Jiang and Newman in 2018. So that's, and yeah, let me focus on the case when epsilon is small, so for today. So that's basically the result, definition, result, and background. So
This is an annealed statement where you're averaging over the H's.
say that again. This is the quantity. Well, this says the probability. I mean, there's only at the 0 temperature, there's only a single probability measure. right? There is no Ising measure. The Ising measure is deterministic. So and the conjugate annealed in this case doesn't really matter much because if you can get an annealed upper bound in these cases. So that also gives you a conjugate upper bound. So far so good?
Well, yeah, maybe you should ask, because I don't, some people are very familiar with this, others are not, so maybe, Jenny, does this make sense to you, or do you have questions? Or?
Good, that's encouraging. Yeah, okay. I'm not going to say more about the motivation or blah, blah, blah. I'm just going to the proof. I hope I can give you some intuition about the proof. I will say a couple of sentences. I don't know how helpful they will be. There were two main ingredients in the proof. One of them is the work from Michael and Burchard, which says for kind of critical-like percolation systems, the intrinsic distance has exponent strictly larger than 1. Another ingredient, another feature of the proof, which may be new, is we consider perturbation analysis in this case. You can imagine that I should have defined something before I said this. Let me define something and then motivate the perturbation analysis. Sorry about that. Let me first reformulate. Let me define CV of as the following. It takes 3 values, plus, minus, or 0. It's plus if both boundary conditions give you a plus. It's minus if both boundary conditions give you a minus. And it's 0 if plus boundary give you plus and the minus boundary give you minus. We use 1 minus 1. And by monotonicity, the other condition, the other possibility will not show up. I mean, for Ising measure, it's a monotone system. So if you have better boundary condition or better external field, then you will always dominate the less good boundary conditions or external field. And then the theorem can be reformulated as I want to show that the origin takes value 0 for the Kc value. This has exponential decay. If you think a bit about it, this zeros has to have a percolation sort of perspective, meaning any 0 in the box, you should be able to find a path of zeros connecting to the boundary. This motivated us to consider the percolation perspective of zeros. And another way, that's why it's linked to the percolation work of Ising and Burchard. Another feature of our proof, I said, is a perturbation analysis. Basically, we want to show 0 is unlikely, right? In order to show 0 is unlikely, a different way to put it, which turns out to be quite convenient, is that if you perturb the field a little bit, a 0 will have to disappear after perturbation. So that's what we are going to use, rather crucially, in the proof. So now let me just do the perturbation analysis.
What's wrong with the intuition that, like, okay, if there's no disorder, the ground states are all plus, in one hand, all minus.
Yeah.
If there's a tiny bit of disorder, then you think the ground state, well, it's mostly plus with tiny islands of minus. So the theorem is telling me that's a bad intuition. That if you're far from the boundary, you can't tell that.
That's correct. Yes, but is there something?
So what? I mean, why is my intuition misleading?
Why would the
This is a good
why would
question.
the
This is a
islands of
good
minus be tiny? What makes the islands of minus tiny?
Well, the disorder is very small. So
But okay, there is some intuition in this case might not be so. I mean, there is some physics argument actually says the opposite of what I'm going to tell you. Not quite opposite, but they have some sort of certain disorder says that these are
Your
power.
argument is going to be good in 3 dimensions.
Right.
Okay.
I didn't talk about.
It's not going to be good in 2.
I didn't talk about 3D. In 3D, then this this is actually not vanishing, even at weak disorder. roughly speaking, even if well, you're even challenging now Michael's result basically for this conversion to 0. Roughly speaking, this means in 2D, the volume is the surface area square, and the fluctuation of the Gaussian disorder is the square root of the volume, which just enough for you to kill the disorder, and this happens in many scales, then you're going to kill the disorder. But intuition can be misleading, so that's what I'm told, and I don't know how to turn that into an argument. Actually, in Michael and Ron's paper, they mentioned this Mandelbrot percolation analogy. We use something similar, but it's not so easy to prove actually that it's dominated by a Fractal percolation process. Because you could think things in different scale and say if one scale the volume actually dominates the surface, you would win, but it's not so easy to actually get that. Doesn't it?
Does this have anything to do with a Merman-Wagner type argument where somehow the disorder is, instead of just having plus and minuses, you could see some sort of continuous symmetry being broken that wouldn't work in 2D and would work in 3D? Is there something?
A simple way to think about this is if you think that configuration constant because there is penalty for disagreement, then the disorder is B. The question is which constant will be B? And the competition is within this approximation between the net field, which is of the Gaussian of the order of square root of the volume, versus the boundary effect, which is of the order of the boundary. The dimension at which the d over 2 crosses d minus 1 is the critical dimension, which is 2. And for the Mermin-Wagner argument, a similar counting leads to 4 dimension as the critical dimension, a continuous version.
Yeah. Thanks for answering the question for me.
Influence percolation, that's another way to think about it.
What happens if you make the boundary weaker? You don't make them.
Well, anything, if plus boundary and minus boundary, if you would agree, then any other boundary condition would agree.
Certainly.
Yeah, because they are sandwiched in between. Okay, so.
One final question. So you mentioned that your result works for Gaussian IIDs. Does the Ising error work for any?
The first work, I think, works for a general class of disorder. These two works with Gaussian disorder. Yeah. You can try to. I'm happy with the Gaussian for now, at least. Any more questions before I proceed? Okay. So let's do a perturbation analysis. I will consider a field H tilde V, which is just HV plus some delta. That's what I do. And delta is going to be chosen. There are two important cases for delta. Delta is naturally going to be chosen depending on n. And there are, if you look at the box of size n, then I'm going to choose delta depending on n. There are two important cases. One is delta equal to of order 1 over n. Another one is delta is of order 1 over n to some power gamma, gamma larger than 1. The importance for the first perturbation is that the Gaussian measure before and after perturbation, they're contiguous to each other. So if you can say anything about the perturbed measure, that translates to some things about the original measure. The second perturbation is very tiny. Well, of course, they are still continuous, more than continuous. It's very close. It's very tiny. After we proved something, after we had some better control of the system, it allows us to say even under this tiny perturbation, 0 has to disappear. And then you see that this gives you a lot of leeway, because that says now for this pretty much intuitively says every single scale, there is a very large probability that the variability, the randomness in that scale is going to make the two things collide, make the 0 disappear. And if this happens for many scales, this is going to give a large power decay. Once you have a large power decay, then it's standard argument to enhance it to exponential decay. That's roughly the importance of these two cases, and that's what we do later in the argument. And now let me, before I present the perturbation lemma, we need some notations. So let C lambda n be zeros. The zeros are with respect to the Kc values. And this is with respect to the field HV. And let's see tilde lambda n be zeros with respect to the field H tilde V. And I want to consider the intersection, because one way to say things would disappear is that the intersection is small, right? So I consider intersection, say star of lambda n, to be just the intersection of the two.
You can write a delta sub v, but delta is, you're changing it on every site?
Say that again?
Your delta H.
Yeah, every single,
Delta sub v.
yeah, for every V.
Oh, it's the same delta on every
For same delta. Later,
delta
yeah,
on
for
every site.
the important perturbation I'm going to discuss.
Doing it on every site.
Yeah,
exactly the same.
Yeah, every side I perturb exactly the same amount. Later in the finishing of the proof, I'm going to do a slightly different perturbation where the perturbation only occurs in the annulus, because I want to decompose the different scales for independence reason. But if we can ever get there, then life is not too bad already. But let's say we just consider the constant perturbation for now. But that is depending on n, depending on which box you look at. Because if you do the constant perturbation, it doesn't make any sense then. Okay. Now, let's look at the lemma. The lemma says that the following two cannot both hold. A is the d of C star lambda m. This is the intrinsic distance in the subgraph on the C stars. Okay, so like consider the subgraph and look at the graph distance in that subgraph. The distance of this between the two boundaries is larger than k, and B is that the C star in the smaller box, inside box, times delta, this is larger than 8 over k of the times the volume of C star in the annulus outside.
Can you draw a picture?
Yeah, I'm going to draw a picture. I can.
Put it all the way up and put the other one down.
Yeah. Okay. So I'm considering this is my box of side length n. This is my box say of n over 4. This is the annulus. This the middle thing is the annulus that I'm a of n over 2. This is lambda n over 2 set minus lambda n over 4. I'm just saying, well, let's first consider the distance has to be larger than n, right? Or n over 2. That's a priori, you know that.
So what is this distance here? What
This is the intrinsic distance in the cluster, in the subgraph. It's like the shortest path of vertices in C star.
Lambdas you've just drawn, those are the two things that lambda over 4 and lambda over
Oh, the distance is between this. Yeah. Thank you so much.
But that distance is in what?
It's in this. It's in my C star.
C star is what?
Is the intersection of the zeros before and after perturbation.
Okay.
Yeah. Of course, a priori, you know this has to be at least n over 2 or n over 4. Okay. Some of order n, right? So if you first think delta is also of order 1 over n, this basically says, well, these two cannot be comparable, because this delta times k would give a constant. This says these two cannot be comparable somehow. But you would imagine this would be comparable. So this would tell you something, actually.
So this distance is a sort of percolation distance, and if it doesn't percolate, then the distance
It's infinite. Yeah, if it doesn't percolate, then it's infinite. Okay. Yeah.
Let's see. I'm trying to understand. What's the second condition mean?
Second condition just means if you imagine that delta times k is equal to 1, that just means what you get inside cannot be too much larger than what you get outside. But you see, what you get inside is something with respect to lambda n over 4. What you get outside can be bounded with something with lambda n over 2, right? And that basically says inside, that basically says when you enlarge the boundary condition by a factor of 2, the probability for the probability for the 0 to occur has to shrink by a large factor. If that's true, then you should have a large power law decay. That's basically what it means.
Say cannot both hold, you mean
What?
there's only a small probability?
This is a deterministic statement. This is the HV in this statement is deterministic. There is no Gaussian here. Okay, now I need to give you a proof. We prove by contradiction. Suppose AB hold. Then we run a breadth first search on C star lambda n. So basically, I just explore the vertices.
What does this mean?
Yeah, I just explore the vertices in C star layer by layer.
Well, what is BFS stand for?
Breadth first search process.
Oh,
Breadth first search expresses.
Okay. Breadth first search.
Yeah, I just consider the vertices with intrinsic distance 0, 1, 2, 3, layer by layer. Starting from well, you could start from origin, but in this case, I want to start from the boundary here, because that's the two things I'm considering. Yeah, I'm just doing the exploration process, and started from lambda n over 4. This is all the zeros, and then we can obtain, because I know that the distance is large. That means I have many layers, right? So at some point, one of the layer the size has to be smaller than the average of the average size of the layer. So I can find a set S that contains all the C stars in the smaller box. That's because that's my source. That's my starting points, and everything is contained in everything is contained in the n over 2 box. And I want, importantly, such that the boundary of S intersect with the C stars. I want this to be smaller than the total volume in A n over 2 divided by the distance. This is always achievable, because this is just a simple averaging argument. And for notation reason, let's denote this by B. Okay. Now, since I know that for S, when you have plus boundary, it's all 1, right? That's what you know. That means if you do plus boundary, think about if you do all minus boundary, look at the difference. You gain from the field. And you also gain from the interactions with the pluses. Okay, I need to tell you what the G is. Well, G of S tau is equal to the pair of vertices on the boundary and the Cassey value for the outside vertex is tau.
HS means what?
HS means sum, yeah. Very good guess. Yeah. You gain the sum for the plus, and you also gain for the interaction with the plus boundaries, and you lose the interaction with the minus boundary. But you would gain the interaction with the zero boundary, because in this case, the zeros with the plus boundary condition is actually plus. Since you prefer plus in this case, that means this has to be greater equal to 0, because otherwise minus is better. Would contradict with the fact that with the plus boundary this is 1. Yeah.
So is that when you flip all the spins in S?
Yeah. If this does not hold, then you flip all the spin values at S, it would give you something better. This contradicts with the minimality of the Hamiltonian. Now, if you think about it, now I increase the disorder. Everything has to increase, right? You could have minuses before, now become zeros, or zeros become plus. But minus become 0, 0 become plus, they would not hurt you. If later I want to consider a minus boundary condition in the tilde version, what really hurts you are the ones on the intersection. Because it is a plus now, but later if you consider minus boundary condition, it will become minus. So okay, maybe from this I want to claim that H tilde S plus. Imagine now I want to in the H tilde S. Imagine now I want to actually look at the minus boundary condition. Sorry, I still look at the plus boundary condition. This is what you gain. So, sorry. I'm looking at the minus boundary condition and looking at what if you choose plus spin with the minus boundary condition. This is what you would gain, and G tilde S plus is also what you would gain. G tilde S minus, this is what you would lose. Since now I consider the minus boundary condition, those in zeros is what you would lose. I claim that this is, I don't know how much algebra we should do. I claim this is greater equal to H tilde of S plus G of S plus minus G of S minus plus G of S0, but then I subtract twice of the edges between S and B. Because the only difference that's making here are the ones in the C stars. Because when you consider from a plus boundary condition to minus boundary condition, those are the ones that changes from plus to minuses, which makes a difference to the interaction. And those are zeros only in one of the configurations. Doesn't matter, because if it was a minus before, it becomes a 0 now. But a 0 gives you a minus, but it was minus before anyway. It doesn't. You don't lose. If it was a 0 before and a plus now, well, now you have a plus. At the beginning, you consider plus boundary have a plus. They cancel each other. Those who really make a difference are the ones in the intersection of the two zeros. So, and I subtract twice copy of that to incorporate the influence of that. Does that make any difference? I could also write down more algebraic facts to why this is true. No? Okay.
No, I'm still getting a little bit lost here. So,
Okay.
Can you just say, is there a way of saying in words what you're...
Yeah, I mean, okay.
Because I'm getting lost.
Yeah. So you look at all these terms.
Okay. I've lost it even with the definition of some of the terms.
GS tau is the...
What is GS tau?
GS tau is like, this is the S, and this is the boundary. Tau, so say tau is plus. GS tau incorporates all the edges that interacts with the plus vertices. GS minus incorporates all the edges that connects to a minus vertex. And so it's also G0, and G tilde is the tilde version of G.
So it's all the edges. I mean,
Yeah, all the edges on the boundary, because that's the influence that you're going to study.
oh, okay. So this ball you've written here is a smaller boundary.
This is my S inside.
Okay, I gotta remember what S is.
S is what I found. It's a subset of the C stars. Does that make sense now?
Well,
There's some surface in between those inner shell and the outer, between lambda.
Exactly that. This is my S.
That's your S.
Yeah, and there's a segment of it is in the C stars. And those are the ones that when you change the boundary condition, that's going to make it trouble for you. Those are the ones that makes it trouble for you. Or the others you don't mind. If it's always plus, it doesn't you don't change.
where is the S defined again?
S is something I found in the exploration process. It's like the first time that you find a boundary that the boundary is small. I want the boundary to be small because this is what I lose. Does that make any sense?
It's going a little faster, but
Sorry. Well, how much time do I have? It's already, I have an hour, so.
You want the number of zeros on the boundary of S to be small.
Exactly. Yeah, because then I want to use the volume to kill the boundary. I want to use the perturbation of the field to kill the boundary. So I want the boundary to be small. And I can do that if the distance is large, right?
Can you pull down the board so we see?
I'm happy to do so. If you believe this, which you may not, I can write down more write down the contain, because this uses monotonicity. The plus can only, if you are a plus before, it can only be a plus now.
FKG to here or what?
I'm using the monotone coupling. When you increase the field, the spins can only get increased.
Yeah,
That's FKG.
That's FKG, right?
Yeah.
Or not?
Yeah. Is that
You're
FKG?
not going to be able to do other spin systems that don't obey FKG.
Okay. I'm using monotonicity. If that's FKG.
I guess that's what it is.
Yeah, I can say right. Yeah. Okay. So I'm using that to argue this line. Okay. If you believe this.
Is there a tilde on the second HS?
Yes, there's a tilde because I just copied it. But now I'm going to use this line to say this is actually larger than the volume of S times delta, because there's a difference. That's what I gained from the perturbation from the field. And what I lose is at most twice of the size of B. That's the boundary. That's the boundary with zeros outside. That's what I lose. But if under my assumption, this is going to be positive, because I assumed that B is small but S is large from my A and B, if you do the calculation. Now, this gives you a contradiction. This gives you a contradiction because this says, even with minus boundaries in the tilde version, you still want to be plus. So this cannot be zeros. Just because you gained so much from the increase of the field, and you only lose so little from the boundary. Does that make any sense? Okay. Now, so this is the lemma 1.
But you said all you said is deterministic statement.
Yeah, those are deterministic. There is no randomness.
You're not using.
I'm not using Gaussian yet, but I will. The Gaussian is not used too much. It's used maybe a few times, not too much. Let me at least show another lemma so that things become a bit more motivated. This board is visible, right? So lemma 2. Lemma 2, I want to show that, let's say I set k is equal to n over 4, and delta is 10 to the 10 times 1 over n. So in particular, the A in my lemma 1 now holds automatically, because the distance has to be larger than n over 4. And I claim that probability, you look at a box, this is of lambda n, and look at some rectangle inside, use some imagination. These are of comparable sides, but let's say I can lose a constant. And this is a rectangle. Actually, I draw the rectangle can be oriented in any direction, doesn't matter. The rectangle, the has to be fixed, but it can be 1 to 100, or I don't care. And now the probability, the event I'm looking at is percolation. There's a crossing through the tiny rectangle. The crossing are the vertices in C. And this probability is bounded away from 1. So this is less than 1 minus delta for some delta only depends on epsilon. You look at the box and you look at the rectangle inside of comparable sides.
You fix the rectangle, or it says there is. What's
You fix a rectangle, of course. You fix a rectangle, and you ask what is the probability there is a zero crossing inside the rectangle in the hard direction.
In the long direction.
Yeah, in the long direction. I want to say this is bounded away from 1. Okay. No, delta just has to be positive. For delta equal to delta epsilon positive. Sorry.
The capital delta. You're not using it, are you?
I'm using it.
When?
Oh, okay. Yeah, these are only in the proof actually. I should have sorry, I should have stated this and then yeah, these are for my proof. I'm just saying we are going to consider this and prove this. The statement doesn't have can delta. You're right. Sorry, that's the confusion I introduced. Sorry about that.
But what's the other box have to do with it? I don't understand. You got two boxes.
This is say you pose the plus minus boundary condition here. Yeah. You need.
Okay.
Yeah. The statement is finally clear? Not yet.
Well, probably, but I'm just trying to make sure I said
So using this perturbation from the capital delta to prove
Yeah, I use the perturbation. You see, I choose my capital delta so that the two measures are contiguous to each other. So if I can say something about either of the measures, I can say something about the original measure. Okay. So here's the proof. So first, let's theta to be some quantile of x that probability, say, c star of lambda n over 4 intersect with lambda n over 8. That's equal to x. Say I want this to be greater or equal than 1 minus 10 to the minus 6. What does this mean? Just means, well, this is just a threshold. If I look at this smaller box inside, I draw another box. If I look at a smaller box inside and consider the boundary condition in the smaller box, look at how many C stars, how many zeros you have. The x is my threshold that is close to 1, but a bit away from 1. Now there are two cases. So case 1, theta is positive because theta could be 0. The 0 is an easy case, I think, because if theta is 0, that just means, well, with very good probability, you don't have intersections, life is easy. So let's focus on the case that theta is not 0. That's the hard case. That makes sense, right? So if theta is bigger than 0, then with probability at least 10 to the minus 8, we have C star with respect boundary n over 4 intersect with lambda n over 8. This is actually larger than 10 to the minus 6 times C star lambda n intersect with the annulus. So there's the annulus outside somewhere. There's some zeros. I want to say with some probability that the zeros inside with respect to the smaller boundary is larger than the zeros outside. Why is that? Because you can cover the annulus by smaller boxes. You have constant many of them. The ones inside and the ones outside, for the smaller boxes, they are independent of each other. So there is some chance, positive chance, for the maximum, for the central box to have the largest number of zeros. That happens with some tiny chance, but I don't mind. If that's the case, then what happens? What's inside is larger than what's outside up to some constant factor. Does that make sense? But now you see something funny occurs, because with the choice of my parameters k of delta, if you look at my lemma 1, A holds, that means B cannot hold. But now B holds, except this is not with respect to boundary lambda n, but with respect to the boundary lambda n over 4. It's not the original boundary. With respect to this boundary, you have more zeros because of monotonicity, right? What does that mean? This holds, but that cannot hold. That just means these two are different, right? If they are equal, then this, if this set equal to that set, then we are done. Then it cannot be the case because it violates the lemma 1. So by lemma 1, there exists at least, that's what exist means, I guess, exists V in lambda n over 8 such that V is in C star and with respect to boundary lambda n over 4, but V is not in C star with respect to boundary lambda n. What does that mean? I have a V here. I know it is a 0 with respect to this boundary, but not a 0 with respect to the boundary outside. Well, in order for a vertex to be not a 0, basically you say it's 1 or minus 1, doesn't matter, it's symmetric. If it is a 1, then basically there should be a component, connected component of 1s that just by looking at this component and the field in this component, it will be 1 no matter what you do outside. That's the certificate. This is the if and only if condition. But now I know that it is 0 with respect to the smaller boundary. That means wait, I know it is 0 with respect to the small boundary, but it is not 0 with respect to the large boundary, right? So in the large boundary, since it's not 0 with respect to the large boundary, that means I can find the component, find a set, so that it's a certificate that it's 1 no matter what you do outside, right? But this set cannot be contained in the smaller box. Because if this set is contained in the smaller box, then it will be plus 1 even if you change the boundary in the smaller box. So that means your certificate, your weightness for this vertex to be 1 has to intersect with the boundary with the boundary of lambda n over 4. Does that make any sense? We know that it is not a 1. We know that it is a 1 with respect to the large boundary condition. In order to be a 1, you just consider all the 1s with respect to the large boundary conditions. So you get a component of 1s. And the boundaries of these 1s are either minus 1 or zeros. But if you consider the minus boundary condition outside, the zeros will be minus 1. But even in those cases, these 1s will have to be 1. That's your weightness that this vertex takes value 1, no matter what, right? And this weightness, this set, has to exist since the value is 1 with respect to the large boundary condition. But this set cannot be too small. If the set is strictly contained in the smaller box, that means even if you change the boundary condition in the small box, I'm still going to be a 1 because this set is not intersecting with you. So the conclusion is you need to have a set, you need to have a weightness, and the weightness has to be very large. Usually the weightness is actually small, but in this case it has to be large. Now we are almost done because This implies there exists a plus or minus crossing from V to the boundary of lambda n over 4. Well, that implies there's a crossing between lambda n over 8 to lambda n over 4. And this happens with a positive probability. By applying the duality, this prevents the annual crossing of zeros in this annulus, you consider. And if you do some other standard trick in percolation, this says the percolation probability in the rectangle cannot be very close to 1. Has to be bounded away from 1. Does that make any sense? I have about 8 minutes, or maybe I don't know. Should I show another lemma, or
So
I don't think we need a proof.
This lemma do we need to keep both lemmas in mind, or
We need the statement of the lemmas,
yeah?
but this is the proof, so we don't need it. I mean, also this is in either C lambda n or C tilde lambda n. But those two measures are contiguous, so if I succeed in one of these measures, I'm OK. So suppose I have lemma 2. Now here comes where I can use actually the result of Ising and the Burchard.
Maybe you should remind us of that.
Yeah. That says, if you have that, then the intrinsic distance has exponents strictly larger than 1. That means the percolation has to be sort of fractal-like.
Wait, can you make a statement? So
OK. OK. It's my Burchard. I don't know. This is 1999. If percolation, you can consider all sorts of you can consider rectangles of all sorts of sides, but as long as they're well separated in a certain way, and if you look at the events that they have a crossing in the long direction in all of these boxes, you need this to be less than to the power of k. So k is the number of rectangles. Then, and this holds, of course, for all scales. Then the distance in the percolation cluster, let's say C is in the percolation cluster, between two vertices is greater or equal to the distance between U and V to some power 1 plus from power alpha larger than 1. Yeah, this is the Euclidean distance, let's say. I think that's what it says. Did I quote you correctly?
Yeah, but basically, what if the probability of crossing is strictly less than 1, it means that it has the probability for obstacles for essentially straight crossings.
You have to take detours in all scales.
On
Yeah.
every scale, then every the statement is that if on every scale you have some probability of obstacle, uniform impossible probability of obstacle against straight, more or less straight crossing, then every connected path would actually be fractal.
it has to have a detour, yeah.
Would have to have detours on all scales,
Yeah.
therefore its length would not be the Euclidean, but Euclidean to power greater than 1.
Okay.
And can you can estimate that power, or that's a minimum?
Yeah, that's one of the things that.
This power is function of delta.
Yeah, it's not explicit, but you can do something to get some bound out of it. Yeah, I think you can, but nobody did that yet.
So for you, the important fact is that that's positive, that's bigger than 1.
Yeah, that's the important fact. Because bigger than 1 allows me to take a delta that with 1 over n to the power of gamma larger than 1. But that means the two measures now are very close to each other. The perturbation is tiny, but even the tiny perturbation would kill the 0. That gives you a lot of information.
So that gamma is going to be related to that alpha somehow, is that right?
Yeah, gamma is going to be related to alpha, exactly. And now just lemma 2 plus AB gives, there is some probability, but the probability can be improved to be so small, so close to 1. So let's just say with the overwhelming probability. You can have a stretched exponential decay, but actually we only need this probability to be larger than any 1 minus some polynomial decay, so some large polynomial decay. But you can get something much better. So let's say this holds deterministically. The distance in the C star in C of lambda n between the two boundaries this is greater equal to n to the power of alpha. Alpha is strictly larger than 1. I can continue, but the time is. So what shall we do?
Five more minutes.
Okay. So I will.
5 after.
Okay, I will quickly tell you the next lemma and tell you how to prove it, and that probably you are saturated. Lemma 3. Now let me fix some large n star. Set k to be n star to some power, that is alpha times alpha prime. Delta is n star to some power minus alpha times alpha prime square. Well, alpha prime is less than 1, but larger than 1 over root alpha. So in particular, all these exponents are larger than 1. I can make such choices. And I consider this perturbation. And I let m star n to be m star n with respect to the n star, because the perturbation is with respect to the n star. This is the probability that the origin is contained in both the 0 sets. If that's my definition, then I have m star n star is less than, say, a n star to the power of minus 6. This is arbitrarily chosen, but I just want to choose a number that is larger than 2. Why is this? Because well, I need the lemma.
This is what you're trying to prove, right?
Not exactly. This is still the intersection. I still need to go from the intersection to no intersection. But now the intersection for two measures that are so close to each other, to go from the intersection to non-intersection is easy. I cannot do that for the first perturbation because the difference is not. The two measures are contiguous but not too close. But now they're so close to each other. Yeah, it's good enough.
So
this is almost the final thing. Yeah. In order to prove this, you just see that basically, I just need to show that compare mn of mn over 2, you decrease by a large factor, and I can consider this for m between n star to some power alpha prime to n, and for all these n's, the k is at least this. The distance is at least this, which is which is large enough because the power is larger than 1. And now I just use the, so condition A holds. So I just use this. I need to say that what's inside.
You use the reverse of that.
Yeah, well, yeah, this doesn't hold, right? I use the reverse of that. This just basically implies the expected version has to decay with a large factor, because otherwise there exists an instance that satisfies B, which violates my lemma. What this means is exactly if you compare boxes of 2 scales, you have to decrease by a large factor, because of my choice of delta and k. Now delta times k is actually very large, so that gives you a lot of leeway. So even if I only do the recursion in the small constant times log n scales, it's enough, because every scale I get a power of n. And now with this, you do more work. There's another lemma to go from the
power to the exponential.
From the intersection to the non-intersection. Now from power to exponential, that's pretty standard. I think everybody knows how to do that, actually. You just consider blocks, and you have to percolate. You have to have enough number of boxes that percolate, but this is very subcritical. I finished. Sorry for the saturation. Yeah.